รับในหัวข้อถัดไปนี้นะคะก่อนที่เราจะเริ่มขอความกรุณาทุกท่านนะคะปิดเสียงเครื่องมือสื่อสารทุกท่านด้วยค่ะสำหรับในหัวข้อต่อไปนะคะเราจะมาพูดถึงแนวโน้ม AI หรือว่า Artificial Intelligence นั่นเองรวมไปถึง Big Data ในตลาด Startup นั่นเองค่ะ Alright, now ladies and gentlemen, we're going to move straight on to the next topic, which is about the artificial intelligence and big data and startup market. Without further ado, ladies and gentlemen, please put your hands together and give a warm welcome to Mr. Nicholas Walker.
Good afternoon. I'm Nicholas Walker. I'm a solution architect at NVIDIA, based out of Singapore. I look after this region, including Thailand. And what really I specialize in is in an area called deep learning, which is a very interesting and now common technique being used to achieve certain aspects of artificial intelligence. Now, we've got a lot to cover. I will try to speak not too fast, but there is really quite a lot I want to relate to you. The first thing is why NVIDIA, who produces GPUs, which many of you might associate the name NVIDIA with gaming, with graphics. So why is NVIDIA here talking about AI? What is going common? Well, what is going common is that a few years ago we discovered that the GPU that are powering advanced graphics and video games could also be used not just to calculate the shade of a pixel, but could also do math, okay? Could also do operation on other data sets, okay? At the end of the day, they're cores and they're doing multiplications and additions and subtraction. So what if we were to be able to use the power of these very fast processors and instead of doing graphics, being able to use different type of data sets and try to accelerate other application. So here we can see the comparison of how CPU speed has been going up over the years versus GPU speed. Okay, you know that we release GPUs very often, but what is important to know is that due to Moore's law, CPUs has not really been able to speed up much because, of course, as you know, the clock speed has been more or less stable for the last few years, and instead the direction that CPUs have expanded is in going multi-core. GPUs are processors that are made of thousands and thousands of very little small cores. Each core less powerful than a core in a CPU, but we can have thousands of them. So if we have an application that can be parallelized, then GPUs can really speed up, sometimes 100x, sometimes 1000x an application. And as you can see, since we started to do this in 2012, when we released some of our first GPUs with Fermi, we had some other before, the speed up and increase has been really incredible. And this is very important. And it's very important. Okay, it's very important because as we're going to see, AI is a very computationally intense application, and so it can be very challenging to apply to our daily life. It can be challenging to be able to use it, for application, unless we have the power to do so. So here we can see that, similar to the previous slide, the growth is also going to continue when it goes to 2020, while instead the CPU is kind of plateauing. It's not enough to say, okay, the GPU is fast. However, there are other challenges to overcome. These GPUs can be very fast, as we claim. They can also accelerate applications. Question is, if I want to accelerate my application, be AI or anything else, what will be the effort involved, right? Because of course I can show you this GPU and tell you, this is the fastest, it's equivalent to 5 servers, okay, in terms of computational power, but it will take you 2 years to rewrite all of the application to make use of that performance. Then of course it will be, people will start frameworks, all of them are supported by NVIDIA, and all of them can be accelerated on our GPUs. And we're also present in the cloud, okay? So of course, you can also experiment by using GPUs in the cloud. Of course, at a cost. Typically, when people use it a lot, eventually becomes more cost effective to do it on premise. Now, as I mentioned, AI, the reason why AI is something that we see in use now, at least when it comes to deep learning, and we've not seen it 10 years ago, is because it really requires a lot of computational power to be able to train these neural networks to perform a task, okay? You know, neural networks as a theory was actually developed in the 60s. So this is not new technology. This is fairly old technology. The problem was that it remained theory and it remained something very academic because nobody had the technology or the computational capability to actually make use of neural networks to do practical tasks that really will help us out, you know, but only maybe simple examples which will not really be useful in everyday life. And since we started to use deep learning in AI a few years ago, we've also seen another phenomenon. We already know it's very computation intensive, but now we also see that every year that passes, as we get better at using neural networks, the complexity of this neural network, the depth of this neural network is increasing incredibly. In terms of ImageNet, ImageNet is a competition, and in this case, they train neural network to recognize objects and images, okay? What is inside an image. So since in 2012 we had the first neural network to compete, and now in 2016 the neural network competing is called Inception V4, and is 350x more complex or more computationally intense than the one just less than 4 years before really, which was AlexNet. So we are making more and more use of this tech for everyday uses, and we're going to look at some of them. But what is incredibly important to understand is that to be able to take advantage of this, we need the computational capabilities. Otherwise, it just won't be possible to make things more complex and create product that can really make an impact in our life. And that's where NVIDIA comes in, being able to provide the computational capability. So, what really some AI example where today, okay, probably either GPUs or of course not perhaps that in your hand, but how some companies have been able to provide services. Some of them you might be using every day that make use of and rely on neural networks and AI. Certainly a common example that many of you might be using every day is Alexa, Siri, Google Assistant. All of these rely on neural networks to be able to provide a good service, both by being able to understand your words and also being able to understand what you want. That area we call it NLP, natural language processing. Because we don't give commands to Siri, we just talk naturally to our phones and we ask things, right? And that is very different than having to remember commands. We talk to each other in a natural way. We might say the same thing in 60 different ways, and of course we want to interact in the same way also with machines if we can, just more natural. So as you can see here, we have quite a lot of different type of use cases, and being able to train the neural network and then also to deploy the neural network and make it as a service, right? GPUs have been critical in this path to make it possible. So let's skip this. So this is an example of an NVIDIA GPU. So I won't go into the technical details of it, but as you can see, we have 5,120 core in our latest GPU. So your typical server CPU has only what, 20 to 30 cores, right? That's where the power comes in. And we have a lot of very simple operation actually happening when we train a neural network for a task. The problem is we have a lot of it. So it's not as much the complexity of the operation, okay? Very often it's addition and multiplication. It's a problem that there is really a large volume of them. And thanks to GPU, we can do this in parallel. And of this kind of GPU, inside a single server. And this way we can take down the speed of the deep learning training from weeks down to minutes or hours. Of course, as I mentioned, it's not just a question of speed or of a chip, okay? That chip has to come with a platform. It has to come, as you can see, with libraries, with application support, and so on, because it has to be usable. So NVIDIA has been investing a lot of effort and money in trying to develop a platform, develop software, libraries, enabling ecosystem, enabling ISVs, so that you can easily take advantage of GPU performance by just either developing your own application with one of our simple libraries, or perhaps just being able to use an ISV that already makes use of them. Here we've got some, for example, list of applications that are accelerated on GPU natively. So typically you'll see an application, if it supports GPU acceleration, once you put a GPU in, you will just see a speed up in its ability to compute, which can go from 4 or 5x to, let's say, even 1000x in certain cases, depending on the application. AI, but we are also gonna sidetrack in also other type of analytics. AI can be used for a variety of tasks, including making more sense of data. Okay, so it is an added tool. Already, many people use machine learning already in data sets. The use of deep learning and neural networks to be able to extract information out of data is also something that is expanding more and more. Here we have many of the typical use cases. However, what is important is that also for people that are still not moved to the neural network type of analytics, they can still make use of GPUs, because there are a lot of other techniques in area in analytics that also can be sped up with GPUs, and you can take advantage of GPUs. Okay, here there's something very, very important. When we talk about analytics, there's a very common standard nowadays, and the standard is that you need Hadoop, really, if you want to do MapReduce, or if you want to work with large data sets. That's the first assumption. The second assumption is that we have to go through ETL in a very standard way. Okay, we got larger volume of data coming in, and data volume is not really reducing, it's increasing exponentially every year. And what we have to do then is, of course, data comes in, and for each data flow coming in, I have to decide the sampling rate, how much to keep, how to aggregate it, okay, to then make sense of it. So there's many, many decisions which take skill, where you can actually also make errors. Our argument is very simple. You shouldn't do that. You shouldn't do data aggregation. You should just store all raw data that you receive from every of your data sources. Now, a lot of people, will think this is, something nearly crazy, but that's the direction we should be working towards. Aggregating data will inherently translate into loss of information, even if it might not look to you, okay, or it might not be obvious initially. And in particular, when we start soon to use more and more technologies such as neural networks, it becomes incredibly important to have more data, because neural networks need data to be able to learn and understand patterns. And sometimes the sampling of data, or things that for us are not correlated, might be correlated, and that might be identified by a neural network. So very important, keep all of your data. And the other challenge, of course, is leaving aside AI. Fine, I do not aggregate data, I have it all. How am I going to query it? Every query is going to take 2-3 hours, to get back, because just the tables are so huge. Well, that's also somewhere where GPUs can come in, because there are technologies such as in-GPU memory databases. These technologies allows us to and then use all those little small cores to cut up the tables and do the sorts in parallel and the filtering in parallel so that we can speed up the query. So now we can replace maybe 40 Hadoop nodes with one server with GPUs. Then it allows us the capability of querying billions of records in milliseconds. And that means interactive analytics. It's no longer a batch job. It's no longer something I submit and I can answer later. I can now explore large data sets without pre-aggregation interactively, which is really the dream of any analyst. This is possible. The technology is out there. The question is working towards migrating towards that. And this is very important. Instead of having a huge cluster of Hadoop nodes, I can just do with a few nodes with GPU acceleration. So of course, less space, less cost, of course, because GPUs have a cost, but they're not as expensive as that. You need less server, less switches, less power, less cooling, okay, less management complexity, and so on. Essentially, you're doing more with less. And here we go, some of these examples. So apart from typical tools that you might see on the left, as I said, we start to use deep learning nowadays for analytics, but there are also non-AI, non-deep learning based techniques, such as, for example, graph analytics, right? We've got companies like Graphistry and BlazeGraph, that these companies are able to accelerate on GPU graph analytics at hundreds X speed up versus common server CPU-based systems. We can speed up Spark as well, some of the tasks. And of course, we can do those queries on billions of records. We have one benchmark, I think it's 7 billion records in a few milliseconds, okay, and hundreds of columns, with companies such as Kinetica and MapD, and Scream and so on. So there are multiple companies that have deployed this technology, okay? So even if AI for some of you is something that you've not adopted yet, I can assure you that more and more companies, including SAP, SAS, and so on, are coming out. Actually, many of them already deployed AI and deep learning into their own products, and this is only going to increase. So you will have to get accustomed to the kind of infrastructure and usage of this application, but also the fact that also for other type of activity which are not related directly to AI, you may still take advantage of that. So here are just some performance showing the speed up. So for example, this actually is an old benchmark, but we can see for MapD, sorry, it's not going to be too clear, that there is a query that for 10 nodes, 10 Hadoop nodes, it takes nearly 53 seconds and only takes 200 milliseconds with one node. Okay, and this actually is an old benchmark, so it's even faster now. So considering that, if you have to manage a data farm, a data lake, or a Hadoop analytic cluster, there's a constant content growth because there's more and more data coming in. How are you going to be able to scale? Can you truly create, new data centers just to be able to do analytics on your data? Many telcos, retail, utility companies, banks are constantly facing these challenges, right? So definitely it's important to be able to look at new ways of doing things, right? And that are not always, for example, the use of Hadoop. These are some of the visualization that you can achieve, and all of these were generated real time from billions of records, so logs and other type of data. In this case, were mostly to do with network data, huge amount of network logs and of data. We also have free libraries, so apart from commercial software, we also make available a library called NVGraph. You can download it for free, and it can easily allow you to be able to represent a graph in GPU and be able to traverse it very fast on GPUs. Now let's go back to AI and see how can GPUs, what GPU product really can help. I already mentioned, that sometimes less is more. And this has been incredibly important in the areas such as analytics, as I just mentioned, AI in general, okay, and also sometimes in HPC. And as I said, this is an example relating to HPC where we can see how for a certain mix of application, they were able to reduce to 1/7 of the power and space and 1/5 of the cost for the same performance, okay? So servers, 13 kilowatts versus 160 Skylake servers, so even the latest. So that is really important. So if an application, now I'm not going to say that every single application in the world can be accessed on GPU, or even that it makes sense, okay? That's not always the case. Any application that can be parallelized, okay, certainly is a very good candidate, and that's where typically ISVs or developers will choose GPUs as the right thing. GPUs are not an alternative to CPUs. GPUs work with CPUs. NVIDIA believes in both, having CPU and GPU. CPUs are very good at doing things serially, one after the other, okay? Very high clock speed, very strong cores, very complex cores. GPUs are very good at doing things in parallel. In an application, you have both of them. That's why you need both CPUs and GPUs, okay? So this is our current product family. We have an appliance to do the deep learning training, so that's the training of the neural network. Those are the DGX1 and DGX2 with 8 and 16 GPUs. We also have a DGX station, okay? If you don't have a data center or you want to somehow keep it into an office environment, it's water cooled and very silent. And so we have a separate type of products that we use for training and product that we use for inference. Well, why is that? Very simple. Neural networks are very similar to people. The training phase is very tough, it's very compute intense, but the inferencing phase is a lot faster. A surgeon can take 6 years of training to get very good at doing, and learning how to do stitches, I don't know. But then when he goes and starts to work, he might do it without even thinking, and it might take him, 1 second. That's a very important difference between training and inference. In training, more compute intense, we have large batch jobs in which we train the neural network to do a task. In inference, we take that trained neural network and we deploy it, so you would call it maybe production, okay, to carry out the tasks that it was developed for. Now, depending on what kind of inferencing you have to do for what, okay, you might have different type of platforms. Now, if you're traveling at 160 km/h, do you want to rely on a 4G connection that goes to a data center server to analyze the cameras, in your Tesla car and, drive your car? Maybe latency and reliability and, life critical aspect of it will not make it possible. So there's many cases in which we want to do inferencing closer, okay, to the data source. And there's many reasons to it. One, the DirectX2 is for cars, for example, is of course because of latency, because of reliability and so on. But there's also other, for example, we use sometimes TX1 to do video analytics, right? Puntai was just showing a lot of example just earlier, okay, of use of AI, and video analytics is a very popular one. But of course it can be very expensive to be able to transmit data from all these cameras in high definition, because you want to have very high definition images to be able to analyze what's happening in the video, right? And doing that over 4G, well, it's going to make the telco very, very rich, but make you very poor. So the TX1 is, for example, a very small embedded system with a GPU inside. It only uses less than 10 watts of power, and it's able to analyze multiple video streams in parallel, closer to the source, closer to the camera, right? And then you can just send the result back instead of sending the whole high definition video. Or send to people that, for example, I work in Singapore and smaller country, very, very well connected. So they very often want to centralize things, right? And if we continue with example of video analytics, then they will have a data center with this type of card, the P4 card, servers full of this, that we have streams coming in and they're being analyzed for whatever they train the neural network to do, okay? So there's a kind of a different offerings for training and inference, because the pattern, the computational pattern is different, okay? Inference, to analyze one image, it takes milliseconds, okay, 7 milliseconds actually. And it can, one of those GPU before can analyze 5,000 images maybe in 1 second, right? So it's a very different type of use case. And inference is for us what we call a hyperscale, a high throughput kind of environment, right? And of course this could be made as a web service. There's a variety of ways to deploy that, right? If you have an app, okay, where you want sure is we want to make it easy for people to use neural networks. So what we did is that we created a single software platform. It doesn't matter if you use one of our GX appliances, or even if you use a cloud provider, AWS, Azure, Google Cloud, the single software platform can run across all of them, and then you decide where you want to run your workload. Now, the reason why you would ask, well, why don't we just do everything in AWS? Why do I need a DGX server? Well, 6 months of usage of this equivalent amount of GPUs on AWS, you already paid back for a DGX server. That's why. If you use it only 5 minutes a month, please don't buy our server. Okay? There's no sale here, so I can say. But if you have constant usage, if you have a team of people that are developing AI-based products, you will need one of those systems to be able. Also because the movement of data, usually they're very large data sets, so you need a system locally to be able to do this. Now go and explore NVIDIA GPU Cloud, ngc.nvidia.com. As I said, there is a lot of deep learning frameworks to be able to develop neural networks. I'm not going to go into the details of them, but we support all the top ones. We support them, and what we do is that we package them in a Docker container and optimize it for maximum performance. So you don't have to worry about compiling and optimizing. You can just get the Docker container. If you have a GPU, it will just see it and be able to accelerate the training of your neural network or inferencing, of course. The other thing, and here we're getting the technical. By the way, can I see a show of hand? Anyone here who has ever worked with deep learning frameworks? Has ever used one? At least one hand, please. No? Really? No, what? TensorFlow. Anybody has ever used TensorFlow in their life or touched it? Okay. All right. Okay, we got one person, so then I can say it. All right. So what we did, because NVIDIA really doesn't want any money, what they did is we developed a software called TensorRT. It has nothing to do with TensorFlow, although now it's actually embedded inside TensorFlow. And what it does is, after you train the neural network, it kind of compresses it, okay, in a way, so that it's more efficient. Which means that to be able to, when you deploy it, you will need less of our GPUs to carry out a service. Let's say that your service is image analytic, right? Without the optimization, one of our GPU can only do 2,000 images per second. After you send the neural network trained through our TensorRT tool, then it can maybe do 2 or 3 times that, 6,000. Then you need only 1/3 of the hardware, right? So good for you, not so good for us, but it's the right thing to do, okay? Because if you can do 3 times X, why should we make it possible? So we made this available for free so that people can really take advantage of maximum optimization for our GPUs. And also, if you're familiar with Kubernetes, we also now support Kubernetes, both on-prem and also connecting to cloud providers, which will make it even easier in the area of analytics, or if you want to really deploy a service at scale, to make use of GPUs and run the service using Kubernetes. Now, let's go and talk about what can we do with AI, right? So I selected just a few examples. The simple thing is use cases for AI are infinite. For every single area of life, for every single industry, there is an infinite number of opportunity or possibilities of deploying AI to optimize, to improve things, and so on, right? So there's really a variety of things you can do. Let's see some examples of people who are already deployed AI in a number of different areas. And I'm sure that some of you might follow the news and might see many things. Now, something that was popular since very early, when people start to play with deep learning, is of course image, okay? Image analysis. Now, side note, there is quite a lot of some people don't fully understand, what can you use AI for, right? The truth is, you can use AI or deep learning on any kind of data. Structured, unstructured, it can be audio, it can be a data frame, it can be text, without AI, it's very easy to find a word in a piece of text, programmatically speaking, but it's not very easy to develop software that can truly understand semantically what is inside a particular image, right? So that's why people focus on those kind of use cases, because deep learning made it very, very easy in a way, at least compared to how you could do it before. And so a lot of focus has been around analysis of images, right? So I could, for example, train a neural network to recognize, flowers in images, and then it can tell you if there's a flower or not in an image, right? This can be very, very difficult to do without deep learning, okay? It can be done, but to be accurate and to implement it, it would really require a lot of expertise and a lot of time. Now, going back to this particular example, there's many, but medical imaging has been another area that's been really, really critical in being able to take advantage of deep learning. Any kind of image, can be used. We now have a whole area in NVIDIA with our project, so-called Project Clara, that focuses on medical imaging and make it as a service. Now, this is really a tool that aids radiologists and physicians, but let's think, how important this is. For Thailand, I'm also working at the moment on a project in Indonesia. Indonesia has 250 million people, right? We all know that preventative medicine is less costly and a lot better than having to cure a disease at a later stage, right? The problem is that nowadays, the cost to be able to do preventative medicine is very high. And also there's a bottleneck. Now the bottleneck, I can assure you very often, is not the machine. People use tablets, and even tablets actually have been sold less and less because people just use the phone. You can do, every year you can do something more with the phone than the previous year, and so it becomes the most reliable, really, piece of equipment in your life. And a lot of people's life really seems to revolve around the mobile phone. So AI will be the next thing, right? And we've already seen it also in mobile phone, having Siri, having Google Assistant, all of these will be assistive technologies that will start to go and rely on, okay? And hopefully they will reduce the amount of menial tasks, repetitive tasks, because of the automation, because the system can predict what we need, even before we ask for it. So I think the IoT and also AI in particular is going to be the next thing when it comes to disruptive technology that's going to alter the way that we live. So if you're a user of AI, if you're a developer, if you're a startup, it's very important to remember that AI is not something for certain industry. It's something that spans across every single area, and so any industry can take advantage of it in a one way or the other. This is very, very important, and you see that it's really booming, and the faster you get on it, the faster you're going to be able to go to market with a product and have a competitive advantage. So it's really critical that people and companies start to explore this kind of technology as soon as possible to be able to remain competitive in the market. Otherwise, other competitors might disrupt things before they can, and then that will be a challenge. Now, this slide actually is not really up to date because many people think that that number will be a lot higher in terms of spend, and it's getting also, I wouldn't say close to trillion, but it's possibly in the hundreds. So there is a lot of spend happening in the technology. Are they 3,000 AI startups today? Well, I think there is a lot more than that. I think that's a very, very, very old slide, I must admit. Certainly in NVIDIA, we have thousands of companies under our Inception program, which is for startups, and we give them a lot of benefit. So please go, if you're a startup, if you're interested in AI, do search for NVIDIA Inception program and register your company. So the potential really is incredibly high. And there is a big ecosystem, you're not alone. You can actually collaborate with other startups. You can just be a component and then integrate it with other companies to make a final product or a final service. So we see here the progress from the early days of research, where mainly a few research centers and universities were playing with AI and trying to develop services, all the way then for it being picked up by companies such as Google and Amazon. Of course, Google, relies now on over 90% of their product rely on AI, okay? And so on. And now we see, of course, the number of companies really infinite, and we have a lot of leaders. I mean, with Alibaba, clearly, which has invested massively in this particular area, and there's many other companies in China, such as Tencent. And also we see also the pharma, or for example, with the vehicles, many of the automotive companies more and more invested in particular in these areas. Okay, so let's do some jargon busting. I mentioned AI, I mentioned deep learning. What does this all mean? Well, artificial intelligence in itself, I wouldn't really call it a technology, but it's something that we're trying to achieve. That there's many aspects to it. There is the cognitive aspect, decision making, memory, perception, emotion. Okay, and the main technique that people have been using so far is a group of really technologies and techniques, which we call as a group machine learning. Okay, the ability of a machine to learn, typically by using data. And within the machine learning techniques, there's one particular technique called deep learning. Now, deep learning essentially relies on ANN, artificial neural networks. And the reason why we use the term deep learning instead of neural networks, for example, is simply because artificial neural networks are something that have been around for a very, very long time, since the 60s. However, only recently, when we had the technology and the capability of using them for practical application, not for experiments or for academia, that we've really been able to take advantage of them for real needs, everyday needs. And so we call it deep learning because we are talking about deep neural networks. Deep neural networks are capable of doing more advanced tasks versus shallow neural networks that typically were only simple experiment and were not really usable for many practical purposes every day, right? So deep learning makes use of deep artificial neural networks to learn from data and be able to perform a particular task. And this is one of the ways that we try to achieve some aspect of artificial intelligence. And we have an example here of a particular neural network, a graphic representation of it. This one is, I don't know if it's AlexNet, I'm not sure which of the network it is. But it was used to for a particular competition to try to classify images from this huge data set and be able to do it correctly. Typically that was being done by other techniques such as humans and also other machine learning techniques, but since 2012 pretty much the standard now has been the use of deep neural networks to recognize subjects of images. So really deep learning, as I said, it really spans across everything. So you have we have many examples here, okay, of potential use cases in a variety of segments or industries. And this is just a few examples. There's really a lot more than that. NVIDIA is also very invested when it comes to autonomous machines, both robots but also autonomous vehicles. We're working very hard in developing very accurate and safe technology that can help us, achieve autonomous vehicle, level 5 autonomous vehicles, which can completely drive on their own and don't need a supervisor. So how, what is the process like when you do deep learning? So you have a training phase where you train a neural network to do something, and to train it you need to use examples. Okay, so think about like a flashcard exercise. So you have, if I want a neural network to be trained to recognize cats, I will have maybe 2,000 pictures of cats in different poses, in different scenarios, different backgrounds. And of course, each image will have to be labeled, right? Let's say cats. Okay, so you have labeled data that will be my data set, and I will use that to train the neural network to recognize. Typically, the more data you have, the more accurate will the neural network be. So that's not the only factor in question, but certainly the amount of data you're using for the training will be very important for the network to truly understand the concept, the pattern, and be able to recognize it. Then when we deploy it. Okay, so after that, then we will have a deployment phase for inferencing, in which we then, of course, use the neural network to do what we're trying to do. So, what NVIDIA uses to ourselves, even because we have a huge cluster of this, in our own facility. We use DGX1. DGX1 is an appliance that has 8 GPUs inside, and it's been specifically designed to perform deep learning training in the fastest possible way. So the advantage, of course, to do deep learning training, which is a very computation-intensive task using GPUs and using DGX in particular, is the fact that I said if I were to want to use CPU to do that, I would probably need hundreds of nodes to be able to achieve the same performance as a DGX appliance, right? So it's not really cost-effective in space, power, and so on. So it's very, very important to use the right technology to do this, and at the moment the best technology to do deep learning training remains the use of GPUs, supporting all of the different type of deep learning frameworks. And because it's so compute intense and it takes a long time, if I'm a startup and I want to train a neural network to perform a particular task, then I will want to try different iteration and verify if I can be accurate and so on. So in those cases, when I do the training, one of the most important things to be able to go eventually to market with a product is to reduce the amount of time it takes to do this training. If on average, I think that at least 100 iterations of training will be required before, in many cases, an individual will have been able to have a neural network that can be used in production. So if you think that each of those iterations takes 1 week to do, it's not really going to be feasible. So what is really important is to be able to reduce that time so that people can do more training iteration and eventually get to their final result. Very often there's some tuning happening, so that's why we have to do the training multiple times, because maybe the data is just not right, or maybe something that needs to be adjusted, right? So unfortunately, it's not just a one exercise, one training, and that's it. It requires multiple instances to refine the network design and correct issues in the potentially in the data set. So that really is the only really way in which you can make this productive, because it may not make people wait all the time, especially if you have a group of people. And of course, you need data scientists as well. People understand data. AI is not really necessarily a computer science problem. It is also a computer science problem, but mainly it deals at the center of it with data. And we need people who understand data and are able to utilize deep learning frameworks and neural networks to be able to train them on data to understand other data. So why DGX is an appliance? Okay, so it comes uploaded with OS and a lot of software, and we really package everything and tune it for maximum performance. And what we do is that we make available very frequently with new updates many common deep learning frameworks optimized to run training on our GPUs, and we package them in Docker containers. So it's very easy to download the latest version onto the DGX and be able to use that. Again, what we try to do is have a turnkey solution that you no longer have to spend weeks trying to set up and tune a system to do deep learning training, and instead focus on the key thing, which is training a neural network to do a task. That should be really the job at hand, not being a system administrator. So we took away all of that aspect, and we made an appliance that you just switch on and start to do deep learning training in 10 minutes. Okay? So when we look at the enterprise, how do we position this, and how do we're going to see how do we apply it. So now that we're getting in there of cognitive computing, it's clear that every system, every product we develop, every application, every service has to be more intelligent, and that's really, really critical. So this next level can only be achieved no longer by hand-crafted algorithms, but only by applying AI type of technologies and deep learning to be able to have better services, particularly in forecasting and predictive analytics, and also being able to do better recommendation and be able to achieve more insight in our data. And the data that we talked about comes from IoT, comes from a variety of sources, And you know, now that we get into AI, the data set is really, I mean, the size seems to be something very, very scary. You know, if you see the word zettabytes, you know, where many people are already scared when you talk about exabytes. But that is the kind of data volumes that we're talking about nowadays. And to be able to make sense of that data, we can no longer just store it, but we need to analyze it on the fly, and we need to be able to use AI to deal with that kind of volumes data. So of course, there are many examples. I think that we have here Mount Sinai, you know, the use of AI to predict particular diseases by using different type of data. The nice thing about AI is that it can make it very easy to correlate data set which might not really be easy to correlate for us, for example. Certainly in medicine, they correlate medical imaging with, you know, maybe blood tests, electronic health medical records, and so on. In cyber defense, there are now systems that can look at the network logs or system logs of many devices and be able to analyze the data in real time to identify very advanced threats, you know, and so that it can be complex attacks happening, not easy to identify, but with AI, they can actually look at the overall system and be able to correlate information and be able to identify more easily when there is an anomaly happening. Of course, improving customer experience and maintaining, you know, a productive service. I mean, certainly there was just a video that recently was released in which a UK company that provides online shopping services for groceries had a series of robots going all over the place that picked up all the items and put them in the basket. So it no longer uses people as pickers to be able to provide even a faster service. And even in Singapore recently, Amazon released a service in which I think within 2 hours it can deliver your groceries. So you place the order and it guarantees that within 2 hours you will receive them. So this kind of you know, ability to interact with the public in a more real-time way, it's something that is becoming more and more common. And of course, consumers' expectations are becoming higher, and you know, companies have to respond to that, providing better services to remain competitive. Weather forecasting, I think this is also very relevant in Thailand, and you know, I've been working in Southeast Asia for many years, and I've also had many contacts with TMD, the local agency for meteorology, because you know, Thailand is a large country. You know, it's also affected by sometimes monsoon, by certain type of weather patterns, and both for agriculture, for transport, for people's safety as well. You know, it's very important to be able to accurately predict weather, and AI is also helping in that. Going to the next level when it comes to weather forecasting, being able to provide more accurate weather forecasts, also with a you know, shorter amount of notice, or even look and better understand the climate in general. Of course, it's also being used for satellite imaging. That's something else, you know. Very, very important and very interesting. For example, analyzing satellite images, right, or aerial images. These are huge images, and it has to be looked, you know, with a human eye. It will be very, very time expensive to be able to go and classify. Now there are neural networks that are trained to look at aerial images and be able to identify this space is a house, this is a tree, this is a road, and being able, of course, to tag and segment images to create maps, really, without having too much human intervention. So again, very, very important for this very, I would say, very, very challenging tasks, because they're very, very repetitive, not always easy to carry out in volume. So how do we go and start? You know, let's say that tomorrow you want to either start a deep learning project, or you're a company, or in a company you want to either use AI, or maybe you want to develop a product using AI, or you have an idea and you want to implement it. So first of all, let's see how the workflow is actually the full workflow of the training neural network. So we start with a model. Okay, this essentially is a blank neural network, right? So think of it as a blank brain. The structure of the network is there, is defined, okay, but there is no data, there's nothing memorized, okay. So we take that, and there are many available online models that are already being used for specific use cases, so someone can just start from that. Very often you'll have to modify or adapt the structure, okay, but that's something you can find online. Then we start with the training. The training, you'll have to use data. Data is critical to be able to train, and how do I know when it's done? Well, there is no progression bar. It doesn't say 100% complete, okay? The way the training works is that periodically, same as people in a school, you will do a little test and check how good it does. And when the test passes a certain mark, let's say that its score is 95%, you decide really, you can stop the training and say, okay, now I give you the degree, you can go to work, right? So that's really how the training works. So periodically you would check the accuracy by testing it with data. And testing it with data that was not used during the training. Otherwise, the same as you go to school, and then when I do the test at the end of the year or a periodic test, I use the same exercises that were on the textbook with the solution. That would not really be fair and it would not be accurate. So we always have to use data that was not used during the training. We keep aside some data only to be used for the test, data that was never seen by the neural network. So when we're done, we've got this trained neural network, and then we can deploy it. We can go to work. And that phase we call it inference. And in inference, we will have data, for example, pictures of cats, that will be shown to the neural network, and the neural network will be able to say, yes, this is a cat, or no, this is not a cat, if that's what we train the neural network to do. So of course there are many challenges in being able to apply these technologies, but these challenges are really being dealt with quite well, so it's getting better and better. So first of all, we need data scientists, we need people that understand this kind of technology, and there is a big demand. They're very highly paid in US, so we need more people trained in the area of data science, okay, to be able to understand data and then apply the neural network technology in the right way on that data. The second one is that this is a still fairly new area, so the algorithms, the neural network models, the frameworks, they're changing constantly, okay? Everything is changing every day, there's something new is refining. So there has not been any standardization yet on one particular type of technology. That might or might not happen, we'll have to go and see. NVIDIA really supports all the top deep learning frameworks, so it's not really a challenge for us. Fast training, as I mentioned, one of the biggest problems people use deep learning is the training.